This is etezdi. I'm a professor of electrical and biomedical engineering at University of Nevada, Reno. This is related to my NSF EPSCoR project for recovering the waste energy in pressure-reducing valves. I would like to thank Dr. Itani and Dr. Dennett of the Civil and Environmental Engineering for allowing us to use this lab. My graduate student for this project is Mehrdad Majidi. I also would like to thank Tony Piazza and Aaron Smith for the setup here. We have a reservoir here, and we use 2 pumps to increase the pressure to 120 psi on the pressure reducing valve. This pressure reducing valve will take 120 psi and changes it to 80 psi to simulate the customer supply system on a 4-inch pipe. These are motor operated valves 1 and 2, and they are controlled by the computer for their operations. This is our generator, which produces an AC power which is converted into a DC power using our converter box. This is pressure reducing valve 2 for simulating the pressure on the customer side. We adjust the flow for the customer through this valve. We have a data acquisition module in here for our computer. The computer has an algorithm in it which will control the operation of our system.
In the first scenario, actually we are simulating the customer demand at a very low demand. Consequently, the MOV number 1 and 2 actually are fully open, and we don't have any generation because the pressure across the generator is not in an acceptable range between 30 to 60 psi. In scenario 2, we need to increase the customer flow by opening the customer valve. In this case, by opening this valve, the customer flow starts to increase, and also the customer pressure starts to drop. So the MOV number 1 needs to control the pressure on the customer side, and when we are increasing the flow, the generator starts to operate because we have enough pressure across the generator. In this scenario, because the pressure is in the acceptable range between 30 psi to 60 psi, MOV number 2 doesn't operate in this scenario. By increasing the customer flow a little bit, we see that the pressure across the generator exceeds 60 psi. And so MOV number 2 needs to operate to control the pressure across the generator and maintain that less than 60 psi, because it is dangerous for the generator to have the pressure more than 60 psi. At the same time, MOV number 1 starts to operate and control the pressure on the customer side at 40 psi. So we have both MOVs in the operational range. In scenario 4, we have a lot of customer flow, so the pressure on the customer side starts to drop. So the MOV number 1 starts to close to control the pressure on the customer side, and at the same time, MOV number 2 starts to close and stop the electric generation because of the customer pressure problem. This problem is actually just for this platform, and it is not the case for the real platform and water stations.
We like to thank NSF EPSCoR for the support of this project.